Well, it's 12:30, so let's get started here. Um, can I ask you, please, just as a favor, if you would please turn on your cameras? It's easier for me to teach if I actually see some faces there, so that I feel like I'm teaching real people instead of just talking to myself. That's always just kind of frustrating to be just looking at a blank screen. Um, welcome to quantum mechanics. So I'm glad you're here. We see most of the class. Maybe a few people will be coming in later. I hope so. Um, all right. So let me just say a few inspirational things to get started. Right. This is a great subject to be studying. And I'm so glad that you're here to study it. Right. So one reason why this is a great subject is that this is really the basis for a lot of modern physics, a lot of research that people are doing at Kent State and everywhere in the world. Um, Quantum mechanics is really the basis for particle physics, nuclear physics, solid state physics, and many other areas. Um, and so this is really the foundation for any research that you might want to do in any of those kinds of physics in the future. Um, in addition to that, quantum mechanics has a real mystique about it, right? That whenever you talk with people who are not physicists themselves, but they've heard of physics and they all know about Schrodinger's cat, right? And so they'll all be asking you about the cat, right? And um, there's a kind of spooky impression of quantum mechanics that it involves this weird action at a distance and wave functions filling up the world, as if you need to understand it by meditation or by taking drugs or something like that. Um, and so I'm going to show you through this semester that that is not the case, right? That, this is a real mathematical, physical subject. And, you study it by solving equations and looking at graphs and that sort of thing. Same as with other areas of physics. Um, it's a great subject. It's also a challenging subject, right? And I will say it's challenging because it brings together a lot of different kinds of mathematics. Really, it combines at least three different sorts of mathematics. One being solution of partial differential equations. Another one being working with linear algebra, and another being probability and statistics. And so it ties all those different kinds of math together. It really combines everything that you might have studied in previous math and physics courses, and draws on all of that. And so that's something that makes a great conclusion to a physics bachelor's degree, because it really brings together everything that you've been studying over the course of the degree. And so, yeah, we'll be putting it all together piece by piece over the course of the semester. Okay, so to tell you a little bit about myself to get started here. So my own research is in liquid crystals, right? And so I got a PhD working in that area and did a postdoctoral fellowship. After that, I worked for the first part of my career at the Naval Research Laboratory. So that's the main lab of the US Navy in Washington, DC. So I have some experience with being a physicist in this government context, which is different from working at a university. And so if any of you have questions about career planning, we can talk separately about what sorts of opportunities there could be that way. And then after 13 years working at that lab, I had the opportunity to move to a senior faculty position at Kent State. Kent State is a real center of research in liquid crystal science, which is my specialty. And so I was really excited to have the opportunity to move out here and to have a different kind of job with being a professor and working with students. I moved out here together with my wife and colleague, Robin Sellinger, whom some of you may also know. That is, that's my kind of background. I would like to take a few minutes to ask you guys about your background and what's your story here. Let me do that. Before I do, I can turn off the recording. I don't need to record all of you. I will say I am recording this class, as I will record all of the classes in case any of you need to miss it or come back and watch something later. So I will be recording all of the classes and posting them on the Google Drive folder that I sent around. Not instantly after class, but maybe it'll be up there a few hours after the class. But I can pause the recording for your own introduction. Okay, I think the recording is back on, and I will try to remember to spotlight myself on this recording so that it will mainly show the picture of me rather than showing pictures of other people, in case any of you don't like having your picture shown on the recording. I might occasionally forget, and then it will show pictures of other people on the recording. If that is a real problem for anyone, let me know and we'll try to deal with it. But I hope it's not a big problem for anybody to have a few words or images recorded. What else? Yeah, so, and with the video, yeah, it's nice for me if you can keep the video on most of the time. I understand if you need to take a break, if you need to go to the bathroom or whatever, please turn the video off for that. But you can turn it back on afterwards. That'll be fine. It really is helpful for me. And I'm just noticing, normally I would be struggling to remember people's names, but I see on Zoom, it just shows everybody's name next to their picture. That is insanely great. I may never go back on campus again. I think I'll be on Zoom for the rest of my life, and it'll just show everyone's name and it'll help me remember. Good, good. Okay, well, what else now? I should go over the syllabus just to make sure that you all have this information. Okay, so let me share the syllabus on the screen. So I trust everybody already received it in the email, and that's how you have the Zoom link, and that's why you're here. Got it. So just to go over this information, Zoom we already talked about. Here is my contact information. So my office is in the Liquid Crystal Institute, room 225. But of course, I am never there, so don't go looking for me there. And there is my office phone number, but I'm never there to answer the phone, so don't call that number. So I'll put my mobile number there. You've got that. Okay, I do answer that one. Um, and also my email address. I do check that all the time. Um, for office hours, I'll say, immediately after class on Zoom. I'm happy to stick around to answer any questions that you have, either about the class that's just finished or about anything else. So just stick around after class if you are available then. If you're not available, then just send me an email and I'll work out a time to meet with you. That's no problem at all. For the course description, this is a standard thing from the Kent State Physics Department. So this is the kind of subject that we'll be covering over the course of the semester. Here are the learning outcomes, the things that we think you should be able to do by the end of the semester after taking the course. The textbook for the class is going to be this book by Griffiths and Schroeter called Introduction to Quantum Mechanics, which has this cover with a nice picture of the famous cat. This is a pretty standard textbook. It is the most commonly used textbook for undergraduate quantum mechanics courses in the US and perhaps in other countries also, but certainly all around the US. I am going to be using the third edition of this book. When I've taught this course a couple times in the past, it seemed like a lot of students were using other editions. Perhaps they could find earlier editions more cheaply in different locations. That is okay with me. You can use earlier editions. They're pretty similar. I will be assigning homework out of the book. When I taught this before and other students were using different editions, we discovered that it's mostly the same homework problems, but they're numbered differently. And so when I assign homework, I will send out copies of the homework problems so that you can make sure to do the ones that I assign and not other ones that might be numbered differently in your editions. In general, I'm going to follow the book pretty closely. I really do follow what's in there, but I can't cover everything that's in there. I can't provide all the details that the book does. There just isn't enough time. So I'm going to emphasize what I think are the highlights of this subject. But I still want you to read the book, and especially to read the sections of the book before I talk about those sections. So that will prepare you for the lectures and prepare you to ask questions about whatever I'm going to be talking about. I can't cover all the chapters in the book. It's too long. So my goal is to cover the first 7 chapters of the third edition. And I may or may not achieve that goal, but I'll do the best I can to get through that amount of information. And that is what I think people would consider a normal first semester undergrad quantum mechanics course in the US. Let's see, for online stuff, I'm going to be using Zoom. You guys figured it out. Good job. um, I I have this Google Drive site that I'm sharing with you all, and I'm going to be posting all the videos there, along with homework assignments, tests, everything else for the course. So I trust that you all have access to that. Did anybody have any problems with clicking on that and seeing something? No problems. Good, good. Okay. Yeah, last semester in a different course, I used Blackboard, but I found it to be kind of a pain. And I think that Google Drive will just be easier for all of us. Okay, so covering math and programming for the class. Um, in general, the math level of the course involves these three subjects that I mentioned. So multivariable calculus, linear algebra, and probability and statistics. Um, these are all things that are covered in the math courses that are the prerequisites for this class. So I'm guessing that you've all seen these things to some extent, but there's a difference between seeing it in a math class and actually using it in a physics class. And so I realized that. I realized that it's a step forwards to go from seeing it for the first time to using these things in practice. And so I'm going to try to go over the math, as if it's not familiar to you, because it's mostly not familiar to you. Um, um, but you guys have to ask questions. And I can just keep accelerating if nobody slows me down. And so you guys have to ask questions when things are not clear. And so I accept that. And things that you want to ask questions about are probably things that other people want to ask questions about also. That's fine. That's for the mathematics with deriving equations. Now, also sometimes I want to do math to calculate things numerically or to plot graphs. And when I do that, I'm going to use this software called Mathematica, which is very versatile mathematics software. It's software that does all kinds of math, both numerical and symbolic. That is, it doesn't just calculate numbers, but if you tell it, differentiate sine x, it'll tell you cosine x. It does that kind of thing. And so I love it. I use it in my research, every day of my life. So yeah, I use it all the time, and I will be using it in this class to demonstrate stuff for you. And so to show you what graphs look like and to make movies and things like that. Okay? I will be posting the Mathematica files that I show you on the Google Drive. Okay? I would like it if you could install Mathematica on your own computer so that you can then download my demonstrations and run them for yourselves. And then you can make little modifications and see what happens. So Mathematica is free with the Kent State site license. Okay? And so I have the website here, which has instructions for how to download and install it. The downloading and installation, those things are actually kind of complicated. They really make a lot of rules associated with the licensing of this software because it's normally expensive software if you didn't have a university site license. And so installing it is really an exercise in following directions. Okay, and so I would like it if you would go to that website and follow the instructions for student personally owned machines, okay, as opposed to university owned machines. And so give it a try. And I think if you go step by step, the installation will work. And then, later on, within a week or two, I'll be getting to some demonstrations that you can play around with. Uh, I'm not expecting that you already know Mathematica. I'm not expecting that you will necessarily love it as much as I do, because no one loves it as much as I do. Um, but maybe you'll learn to love it a little bit. Um, but whether you love it or not, maybe it will actually be helpful for illustrating some of the points about biomechanics, and that's what I can hope for. And the way that most people learn it is by taking software that somebody else wrote and making modifications to it. So that's what you can do here. For grading, here's the formula that I made up. I'm going to be giving about 10 homework assignments through the semester. And so that'll be 20% of the grade. And then one midterm, that's 20%. The final is 45%. And I said 15% for class participation because I really do want to give you an incentive to say something in the class and to let me know about what you're thinking and what's clear or not clear as we go along. And otherwise, it's just too boring, boring for me. I don't care about anybody else, but boring for me if I'm just the only one who's talking. And so it's good if I can take a break and have some of you talk as we go along. For the midterm and the final exams, we're all still adapting to this pandemic style. And so normally I would do exams in class, but I can't stand this business of watching you guys take exams over Zoom. Some professors do that, but I don't especially like it. And so instead, I think I'll do a 24-hour take-home format for the exam. And so I have a couple of tentative dates for the midterm and the final that are up there, but these are subject to change depending on how things come along. And so if any of you have important conflicts that make you want to propose a different date instead of those, I'm willing to listen to requests like that. I also have a few official policies that I'm supposed to include in the syllabus. Everybody is supposed to include these in the syllabus. And so there's an official policy about how to register for the class. There's an official policy about not cheating. There is an official policy about students with disabilities. If you have any disabilities, please take care of that with student accessibility services. And there's a student survey for the end of the semester that you'll do online. Are there any questions about any of these official policy things as we go along? Please, anybody has anything?
Quick question about the final exam.
Mm-hmm.
Is it cumulative or is it going to cover after the midterm?
It's cumulative. It'll cover everything. Yep. And the subject is really cumulative. I mean, the subject really has everything that builds on what comes earlier in the semester. And so, the exam necessarily has to be that way. you know, I mean, it's not like a history class where the first semester is before the Civil War and the second semester is after the Civil War or something like that. And so, yeah, the subject has to be cumulative in that way. Okay, well, any other questions?
Yes.
Mhm.
Where would you want us to turn in assignments and exams? Just your email or?
Just email to me.
Okay, thank you.
Yes, yes. And yeah, so when you do homework, some people have fancy ways where they write on a tablet to do the homework assignments. If you have anything fancy like that, sure, go for it. That's great. If you don't have something like that, if you want to just do your homework on paper, you can scan it and send it to me. Okay, so ideally, if you have a scanner or a multifunction printer and scanner, that's great. I mean, that makes the nicest looking scans that are easiest for me to read. If you don't have something like that, you can use your phone. And I'm guessing that most of you have smartphones with cameras that can do it. It's best if you can use some app that's especially designed for scanning documents. There are apps like Adobe Scan or Dropbox that have special features so that you're not just taking a picture, but it knows to format the output so that the white paper really looks white. It doesn't just look dark gray. And it formats things so that it knows the paper is shaped like a rectangle. And so it fixes the proportions to make it look like a rectangle, not like some other kind of trapezoid. Some of these apps are free. It's nice for me if you can use them. But I won't say it's obligatory. So if the only thing you can do is take pictures with a regular camera, okay. But I prefer if you can actually make a PDF file that looks a little bit nice and it's easier for me to grade. But then yes, just to email to me. You don't have to do anything else. Good, good. Anything else practical? No? Okay. All right. Well, if anything comes up later, just ask later. That is totally fine. Okay, so let's get started with the real science here. Okay, so for this, I am going to stop sharing the syllabus and start sharing my iPad. Okay, I can do this. So I stop sharing the syllabus and then I turn on my iPad and I go to Good Notes app. Okay, and then let's see. Go share iPad via cable. And does it work? Do you see something there? See a blank whiteboard. Okay, good. Let's try this. Welcome to quantum mechanics. Can you read this? Yes, fantastic. We're in business. Okay. As I said, I'm going to be following the textbook by Griffith. And I generally like this textbook very much, but I don't so much like the introduction to the textbook. And that's because in the introduction, they really just dump a lot of stuff on you all at once without really explaining where it comes from. So I want to take a few minutes to sort of talk about what are the basic things that they dump on you in the first couple of pages and where do they come from. So in section 1.1 of that book, they tell you a lot of things, okay? So these are things that might be surprising if you haven't studied anything about quantum mechanics before. Okay? So number one is the idea that particles are described by a wave function. So in classical mechanics, you're accustomed to saying that a particle has a position and a velocity and an acceleration, right? These are the concepts that you start learning in a class like university physics. Right? And so now in quantum mechanics, we're saying, no, it's not those things. Instead, what it really is a wave function. Okay, which we write as a psi of position and time. Just to help you out with my handwriting of Greek letters, this is how I write the Greek letter psi. So this is the capital version, okay? The lowercase version, which we'll also do later on, is like this. Psi of x and t. And American physicists pronounce this Greek letter as psi. I have no idea what Greek people actually say, but American physicists say it as psi. Okay, so that's one thing they tell you right at the beginning of the book. And another point is that this psi is a complex number. That is, a number with a real part and an imaginary part. Another point is that the physical meaning of this wave function is that the absolute value squared of this psi is the probability density. That is, the probability of finding a particle at a certain position at a certain time. And then a fourth thing they tell you is that psi, this function, evolves in time following Schrodinger's equation. So this is Schrodinger, okay, this little symbol right here, that is a couple dots over the O, that's an umlaut, that's a German accent mark, and it makes the sound be something like Schrödinger, I guess, for German speakers. I'm going to write his name about 1 million times over the course of the semester. And so I will usually just abbreviate it rather than writing out the whole thing. Okay, so Schrodinger's equation, it looks like this, okay? And so it says IH bar times the partial derivative of psi with respect to time is negative h bar squared over 2m times the second derivative of psi with respect to x plus v of x times psi of x in time. Okay, so let me tell you what are all the symbols in this equation. Okay. So here, I is the square root of -1, right? That's the basis of complex numbers. H bar, that is Planck's constant. Well, it's the original Planck constant, h, divided by 2 pi. And this is a fundamental constant of physics, which has a value with certain units. It is 1.05 times 10 to the minus 34 joules seconds. So that is the H bar, which is here and also here. Okay. The M there is the mass of whatever particle we are studying. For example, an electron. And this V of x is the potential energy function. I'm going to be going through all of these things in more detail, so don't worry about that. Now, these things are all just right at the beginning of the book. And, I read this and I said, whoa, way to blow me away on the first page here. So where do all these things come from? And why should I believe that they are true? Well, so the first of these things is really an experimental fact, right? That there are a lot of experiments in early 20th century physics, which demonstrate that particles really do have behavior that's a lot like waves. And let me show you one example of that in a video. Okay, so I need to stop the iPad and start up my browser to show a video off of YouTube. Okay. Is this going to work, or am I doing too many things? Okay. All right, this is going to work. So if I show marks, okay. So I'm going to bring up YouTube, and then I want to share my Safari. Do you see a YouTube thing here now? Yes, good. Okay. Now, is it actually going to open?
Now we are looking at the detector playing on the monitor.
So this,
bright spots.
Okay, let me explain what's going on here. This is an experiment from the Hitachi lab. Okay, so in this lab, they are doing a double slit experiment. Okay, so here is a picture, a schematic picture of their experiment. Okay. So this is an experiment where they have a source of electrons up there. Okay. And the electrons then pass through this setup, which has an obstacle. So the electrons can go on one side or the other side of the obstacle. So this kind of a setup is like a double slit experiment in optics, which you might have seen in university physics or other kinds of classes like that. Okay? So you know when people do a double slit experiment in optics that they see an interference pattern, right? They see that the light waves that pass through one slit interfere with the light waves that pass through the other slit. These waves then can hit a screen and they make a pattern on the screen showing that there's constructive interference in some places and destructive interference in other places. So you see a pattern of light and dark. And by analyzing that pattern, you can learn things, for example, about the wavelengths of light. Okay? So now, these guys at the Hitachi lab are doing the same kind of thing with electrons. Okay? So the electrons pass through this setup on one side or the other side of the obstacle. And you might think if the electrons are particles, some of them will go one way, some of them will go the other way, right? But maybe you'll see a simple addition of those two things on the screen, okay, when they hit the detector. But in fact, they see something much more complicated, okay? And so if I can go back to that video, come on. If I can go back to that video, you will see what's showing
Now
up
we are
on
looking
the
at the
detector.
detector plane on the monitor.
Let's see. Do you hear the
Bright
narrator
spots
talking?
appear here
You
and
do.
there.
Okay.
These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two.
So to pause for a second, you can see with the way the picture looks now, it looks just kind of random, right? It looks like, oh, electrons hit the screen in a whole bunch of different places. So it looks like particles, right? It looks like each electron is a particle and it hit the screen someplace and you see a whole bunch of those bright spots. Right? But now let's see what happens
Since
when
electrons are
there are a lot of
detected
them.
one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biboson, thus creating a uniform distribution without any interference when accumulated. Under such condition, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
Okay, so here you get a pattern that's showing up, right? And so you can see a pattern that really does look like an optical interference pattern, right? This is similar to what you might have seen when you're studying optics in university physics or E&M or classes like that, right? Where there's a bright region. Do you see my mouse on the screen? Yes, okay. So there's a bright stripe, okay, and then it's dark, bright and dark, alternating like that. So this is an image which we could see appearing one spot at a time, right? We could see it where you can see one spot and then another, where it looks like each spot corresponds to a single particle, a single electron. But when you add up a lot of them, there are more electrons in some places and fewer electrons in other places. And so that gives the impression that this is a probability wave, right? That there's some probability of electrons which is distributed in a complicated way across the screen, right? That you see some alternation between higher probability and lower probability regions. Okay. And so, there are a lot of experiments like this sort of experiment has been done for 100 years. I especially like this Hitachi video because it shows the pattern occurring, one electron at a time. And so you can really see both the particle aspect and the wave aspect in the same experiment. You can see how there are a lot of particles, and the whole ensemble shows this interesting probability distribution, right? And this gives the impression that there must be some wave-like behavior even associated with the distribution of particles. So now I'll go back to my iPad. Okay, back to the iPad. Now, what about Schrödinger's equation then? Oh wait, I don't have the iPad up here yet. Share. Okay, iPad. So that is some kind of experimental motivation for thinking that there's something about particles that's related to waves. And I'm guessing that you talked about this in the modern physics class also, right? Which most of you have taken before coming here. And so modern physics was giving some of the experimental justification for thinking about particles like waves. That's a justification for this idea of waves. And if there are waves, then you'd say, well, there must be some kind of wave function, right? Something that's adding up and something that can make interference by having places where you add up positive or negative numbers. And maybe that's a justification for this idea of a probability density also, that there's a varying probability of having particles in different positions. But now, what about the Schrödinger equation? Okay, so where does this equation come from? The textbook doesn't really talk about a motivation for this equation. It just says, look, here, this is our new favorite equation. Right? This equation is going to take the place of F equals ma that you've gotten to know and love over the course of your previous physics classes. So I went back to Schrödinger's paper, his first paper in English from 1926. He had a few other papers in German before that. But if you look at Schrödinger's paper in 1926, all right, so what's the story there? Like, where did it come from? Historically, this was really a weird kind of brainstorm that he came up with. This was the kind of thing that a lot of physicists were worried about in the early part of the 20th century. And so for the Christmas vacation in 1925, he just went up to a mountain cabin with his girlfriend for a couple of weeks, and he came back and he had the answer. And so it's just like inspiration hit him up on the mountaintop. So I looked at the paper to try to think, what was he thinking about? And as I understand it, he was thinking a lot about analogies with optics. So, you know that there are at least two different ways to think about optics, which you have learned about in different physics courses in the past. Okay, so one way to think about optics is the geometric optics, where you trace rays. And so in geometric optics, we would say, maybe there's a source of light here, and somebody has an eye, or let's say a detector over here. And then we think, oh, well, there's a ray that goes from the source to the detector, right? Or maybe there's a mirror. And so you have a ray that comes down here, and then it has specular reflection and goes like that, right? Or maybe there's a lens. And you have something that passes through the lens, and it gets refracted and heads towards the detector, right? And so you learn about things like Snell's law for how the refraction goes. Okay? So this idea in geometric optics is all based on the notion that light is a ray, and it's following a particular path, and then you can figure out what's the geometry of a path. Okay. So that's how you learn about optics at the beginning of studying physics. Okay. And then later on, as you continue in physics courses, you get to wave optics. And you say, well, light isn't really just a ray. It's more complicated than that. Light is really a wave. And so then you see, what is the wave coming out from a source? And then you can't just be tracing rays anymore, but instead you have to solve Maxwell's equations. All right, and Maxwell's equations describe what is the electric field as a function of position and time, and the magnetic field as a function of position and time. Okay? And so everything becomes more complicated, right? Because it's not just a single path that you're following, but there are these fields that are everywhere in space, and you have to calculate them everywhere in space. Okay? But still, that doesn't mean that geometric optics is wrong. Geometric optics is a limiting case of wave optics. That is, if we have lengths which are much greater than the wavelength of light, then then I should put it the other way. Then wave optics reduces to geometric optics. That is, if we have lengths where everything is much greater than the wavelength of light, then wave optics predicts the same thing as geometric optics. So you don't have to forget geometric optics. You can use geometric optics most of the time, but you can't use it all the time. Right? Sometimes geometric optics fails, and you have to use wave optics, which is more fundamental, right? And wave optics will tell you what's going on in a broader kind of situations. Okay. So Schrodinger's article from 1926 that I read, it talks about optics a lot, and it says, well, we know that the behavior of electrons is a lot like optics, right? That electrons have this sort of double slit experiment, for example, right? And so Schrodinger was thinking the same way that geometric optics is an approximation to something with waves, maybe classical mechanics is also an approximation to something with waves. Okay? So it's sort of an analogy problem like on a standardized test, right? That is, we want to say geometric optics is to wave optics as classical mechanics is to something. That there's an analogy that there must be something out there that reduces to classical mechanics the same way that wave optics reduces to geometric optics. Okay? So Schrodinger had the idea there must be some wave description out there. So what could it be, right? So quantum mechanics, or quantum mechanics must be the thing that goes in this blank. Okay. But it's not enough to say quantum mechanics goes into this blank. There must be some set of equations to solve to get quantum mechanics. And with wave optics, we know that means solving Maxwell's equations. And by solving Maxwell's equations, we'll get what is the electric field and the magnetic field everywhere. And that's how we make predictions. Okay, so Schrodinger figured there must be some equation to solve that gives us this probability wave, the psi of R and T, well, in 3D, or psi of X and T in one dimension. Okay? So there must be some equation that we have to solve. Okay? And so when he was up on the mountaintop, he was thinking about, well, what could the equation be? And what would it need to do so that it would reduce to F equals ma in the situations where classical mechanics works. Right? And so, he has lots of theoretical considerations there, which I am not going to talk about. But that's how he came up with the equation. Okay, it was that sort of reasoning by analogy to say what sort of an equation would reduce to what we need. What sort of equation would turn into F equals ma in the classical limit, but it would still give us the wave behavior that we're looking for. So that is, my kind of reconstruction of what he must have been thinking that would maybe make the equation seem at least a little bit plausible to you. Now, the next thing that you might be wondering about is why a complex number? Why should we be thinking about the wave function as a complex number instead of a real number? Well, again, I'm just going to speculate a little bit about what the motivation could be there. Okay? And what I think it is that it has to do with how to make a wave equation. Okay. If you have real numbers, then the standard wave equation that you might have seen in other courses, that is second order in time. That is to say that the wave equation involves a second derivative of some function with respect to time. All right. Have you seen equations like this in other courses, right? For example, for sound waves or waves on a guitar string, right? You might see a wave equation that says this is equal to a velocity squared times a second derivative with respect to position. I'm not seeing a lot of looks of recognition. Maybe not. Maybe you haven't seen that. Yes, maybe so. Okay. That's how it normally works with real waves. Okay. But if you have a complex number, then you can have a wave equation that is first order in time. That is to say, the derivative of something with respect to time, the first derivative with respect to time is equal to something. And that is the form of Schrodinger's equation. So I think he wanted to say that the wave equation would be first order in time, not second order in time. And the reason for that is that if you have an equation that is second order in time, you need two initial conditions. That is something like, what's the initial position and the initial velocity? But if you have an equation that is first order in time, you only need one initial condition. So that is, if you know what is the wave function at time t equals 0, that's all you need to get started with. That will tell you everything about the future. And so that is a special feature, right? It is a special feature so that the wave function, that's all the information there is. There's nothing else. Okay? And so that was, I think, part of what Schrodinger's goal was to set up the theory so that you only needed the wave function and nothing else. You don't need to say anything like, what's the initial rate of change of the wave function? So that is something which works if you have one complex function. It could also work if you have two real functions. But, you know, if you have two real functions or one complex function, it's sort of the same thing, right? Because a complex number is a lot like a real part and an imaginary part. And so it's actually, once you get used to complex numbers, it's easier to work with complex numbers than it is to work with two real numbers together. That, I think, provides some motivation for this notion of a complex number. Okay, so this is my explanation of some of these things that go into like the first page or 2 pages of the Griffiths textbook. Okay, so both here are a couple of experimental facts, the existence of a wave function and the probability density, and then some motivation for Schrodinger's equation, and some motivation for the idea of working with a complex number. So in the rest of the semester, I'm not going to try to prove Schrodinger's equation. I'm going to use Schrodinger's equation as the starting point. And then I'm going to work out the consequences of Schrodinger's equation. And one of the consequences is going to be to see, oh yeah, it really does reduce to classical mechanics in the right limits. So the same way that wave optics reduces to geometric optics, we really can say that in certain limits, quantum mechanics predicts the same thing as classical mechanics, but then it also predicts a whole bunch of extra stuff too. Right? And so that's what I'm going to be going over beginning in the next class, which is going to be on Thursday, the day after tomorrow. Okay, so I will stop for here. And of course, I'm happy to stick around and answer any questions, either scientific questions or practical questions, whatever's on your mind. And otherwise, I'll see you guys on Thursday.